Test, 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 test. All right, we are good to go. Double check here. All right. Welcome to another stream here. And today we're going to be looking at OpenAI's recent release of PointE. PointE is a generative AI model for point clouds. Point clouds are a type of 3D format, but they're not a mesh with a texture, which is kind of the accepted 3D format. So point clouds are usually more common in robotics and autonomous vehicle applications because it's generally what you get from LiDARs and structured light sensors. But you don't really see people doing 3D modeling in point clouds, for example, or any kind of video game doesn't really use point clouds very much. But it is kind of an interesting choice of paper, and excited. It has a lot of stars, very quick. Over 1,000 stars on their GitHub repo here in a relatively short amount of time. When I found this actually last night, there was only like I think 900 stars, and then overnight it had like doubled. So quite a lot of stars. Also MIT licensed, so again, you can use it in your business if you want. And very quickly I was looking at the setup and I see that it has clips, so I'm assuming this is all based on the clip embeddings. As we've seen in kind of many of the generative papers that we've been looking at, the clip embeddings are a super popular latent space for images and text, and using text to generate images and vice versa. So yeah, without my cat is meowing at me. Without further ado, let's just get straight into it. So we have PointE, a system for generating 3D point clouds from complex prompts. It's a very recent paper, 16th of December, 2022. You have a variety of different authors here. They're from basically OpenAI and SF. So text conditional 3D object generation. Typically require multiple GPU hours to produce a single sample. This is in stark contrast to generative image models, which produce samples in a number of seconds or minutes. In this paper, we explore an alternative method for 3D object generation, which produces 3D models in only 1 to 2 minutes on a single GPU. Okay, so right off the bat, they're kind of arguing for a speed advantage. They're saying that this is faster. That's not necessarily a good sign, because people will kind of show the best thing that they have, right? They'll put their best foot forward, and if the best foot forward is that it generates very quickly, that tells you that the quality isn't necessarily great. And I would also say that a 3D model is different than a mesh or point clouds. Point clouds are not the same thing as a 3D model. Okay, our method first generates a single synthetic view using a text-to-image diffusion model and then produces a 3D point cloud using a second diffusion model, which conditions on the generated image. Okay, so it's like a two-part pipeline here. While our method's still far short of state-of-the-art in terms of sample quality. Okay. So, I mean, they're honest here. I like that. I like the honesty here where it's like, hey, it's not super high quality, but they're also just doing point clouds, which to me is kind of almost like orthogonal to mesh and texture generation. So true 3D model generation or NERF generation, as we saw yesterday. We release our pre-trained point cloud diffusion models as well as evaluation. Okay, that's good. They do release them. I think that's good. Texture generative, natural language description. Okay, variety of papers. These are all relatively new. That's the current state of AI right now, is that the introduction and historical work section is just a bunch of 2022 and 2021 papers. This all just moves so quickly that you're referencing papers that are less than a year old. Democratize 3D content creation. Yeah, so they basically break it down into two types of categories here. So they have methods which train generative models directly on paired data, so text and 3D. I would say this is a little bit more unusual. I would say most of what we've been seeing on this channel is kind of the second one here, leveraging pre-trained text-image models to optimize differentiable 3D representation. So I would say this is kind of more popular, and this is better because you can use Clip, which is MIT licensed, and then you can just condition whatever you want on that Clip embedding, right? We've seen a variety of NERF papers that condition the neural representation that is a NERF, right? It's like it's a 3D file format, but it's not a real 3D in the way that you would think it is. And they condition that on Clip embeddings and so on. We first sample an image using the text-to-image model, and then sample a 3D object conditioned on the sampled image. Both of these steps can be performed in a number of seconds, okay, but on what type of GPU? If it's anything above a 3090, maybe we can slap them on the wrist for that. For our text-to-image model, we use a version of Glide, and for our 3D image model, we use a stack of diffusion models. Okay, so you have here their high-level overview of the pipeline. First, a text prompt is fed into a Glide model to produce a synthetic rendered view. Okay, so you're feeding this text. It's going into this fine-tuned Glide model, which takes this text and converts it into this Corgi image. And then you have a separate model, which they're calling their point cloud diffusion stack, and that actually generates the point cloud, or diffuses it out of noise, more likely, right, since it's a diffusion model. Corgi wearing a red Santa hat, multicolored rainbow pumpkin, an elaborate fountain, a traffic cone, small red cube sitting on top of a large blue cube, the famous avocado chair. So this is I think one of the first Dolly, maybe the first Dolly paper, one of the kind of more memey famous examples was the avocado chair. So this is kind of a reference to that. And then, of course, the yellow rubber duck is always a classic in any kind of computer science, right? There's the whole rubber ducky debugging reference, so just some memes. They have a novel transformer-based architecture. Okay, interesting. We find that our system can often produce colored 3D point clouds that match both simple and complex text prompts. We refer to our system as PointE since it generates point clouds efficiently. So that's where that name comes from. Okay. Our method builds off a growing body of work on diffusion-based models. Follow the Gaussian diffusion setup. Okay, we aim to sample from a distribution Q of x0 using a neural network approximation p theta of x0, right? So ultimately a neural network, you're just there, it's a function approximator, right? It tries to match the input and the output of some function, and you don't need to know what that function is, and that's why neural networks are very good, because you can just mathematically define some function and then the neural network will over time approximate that. So the theta here is the weights of the neural network, so it's the parameters that define that neural network. They're using a Gaussian diffusion, right? So these diffusion models here, like the one that they're using in this part here, point cloud diffusion, what they're really doing is they're adding noise and then they're removing noise. So it's more that they're learning. You could think of it like the white static on your TV. Maybe that's an old reference, but basically you add a bunch of noise and you learn to remove that noise. So here we have the normal distribution, right? This capital script N is basically the symbol for a Gaussian distribution, and this first part is going to be the mean here, and then this is going to be the standard deviation. So beta is the noise schedule here. So depending on where you are in the noising process, right, for these diffusion models, you're adding and removing noise, but you're not doing that in one step. You're doing that iteratively over a bunch of steps. So you add noise, add noise, add noise, add noise, add noise, and the number of those add noise steps is T, capital T, right? You have a total of T of those, and the amount of noise that you add is going to change over time, right? Initially you might add more noise than at the end, and every time I say add noise, realize that you're also removing noise. So it's like you're adding noise and then you're learning to remove that noise, and then when you actually perform inference with a diffusion model, you only remove the noise. We employ a noise schedule such that by the final time step, t equals t, the sample x of t contains almost no information, i.e. it just looks like noise. Ho et al. Note that it's possible to directly jump to a given time step of the noising process without running the whole chain. Okay, so this is just a standard Gaussian normal distribution here, centered on 0, with a standard deviation of identity, which is basically just 1 in a multidimensional space. And your alpha hat here is multiplying from step equals 0 to t. This capital pi just means, it's like the capital E, it's like the big summation symbol, but it means multiplication instead of summation. So you're summing 1 minus beta t, right? And beta t is the noise schedule. So if you want to know what the alpha at a specific time step is, it's just the beta at like however many time steps before that it is. So it's almost like the way you would calculate kind of the discount factor in a reinforcement learning problem. And yeah, the x at time t, which is x is the sample. In this case, it's going to be a point cloud. But in, for example, in stable diffusion, it would be the actual image. Is some combination of the original image and then the noise, and then the amount of noise and how much of the original image is based on the step. So again, they're approximating here x t minus 1. So the image at time t minus 1 condition given the image at time t. And that's the function that they want to learn. And there is some perfect function for that, right? But you use a neural network to approximate it. And of course, they start with random Gaussian noise at the very end. And then at the very beginning, you're going to have your noiseless sample. A carefully designed second-order ODE solver provides a good trade-off between quality and sampling efficiency. So this is a paper that we read earlier in the year, and basically it was this guy, I think Haras, he's like very good at math, and he just went through and combed the original diffusion papers and said, hey, there's actually a couple different parts of this diffusion process that you can actually project them to a more abstract kind of concept, and then within that abstract concept you have a little bit more freedom in what you're choosing for your first order and kind of second order samplers and how the noise is added and so on. So I think that's what they're referring to here, is that kind of using the better version of diffusion models that kind of came from a more theoretical math intuition rather than the original ones. Okay, several guidance strategies. So you have classifier guidance, where gradients from a noise-aware classifier are used to perturb every sampling step. If classifier-free guidance, wherein a conditional diffusion model is trained with a class label stochastically dropped and replaced with an additional null class. Okay, so you see here, this is the same as we had before. Over here, p of theta x sub t minus 1 conditioned on x sub t, except now you have this additional y. Let me close that. Right here you're also conditioning on y, which is the class label. And one thing that we also saw is that they also they'll kind of drop out. They'll randomly replace this class label with a null, and then you can basically trade off like this, right? So you can say, what is the image when I condition on the image at time t when I condition or the image at time t minus 1 when I condition on the image at time t and then the class label y, and then the image at time t minus 1 when I condition on the image at time t and then a null class. And that kind of gives you the ability to trade off between something that's closer to the class label versus something that is more generic, just more denoising versus denoising in the direction of a specific label. All right. We employ using the drop probability of 0.1. I don't recall what the drop probability was on the original paper where we saw this, but 0.1 seems a little low. I feel like I recall it being 0.5, but I don't know for sure. Okay, you have some original point cloud VAE stuff. (2017, 2014, 2013). So these are all like within the age of deep learning. Okay, so one thing that's interesting is our models also produce RGB channels along point cloud coordinates. So each of these dots within a point cloud, right? There's a coordinate, right? So you can see how it's made out of these little balls. Each of those little balls has some X, Y, Z position. But then what they're going to do in this paper is not only are they going to predict the XYZ position, but they're also going to predict the RGB. So there's going to be 6 total numbers that define each of these dots, right? The actual size of these spheres and like the reflectivity and stuff like that, none of that is defined by the model. That's just all kind of hard-coded in whatever visualization tool they used. Growing body of work explores the problem of 3D generation. Yeah, train a GAN that directly produces 3D meshes. Generates complete 3D scenes by learning a representation that decodes into nerfs. Yeah, this is the paper that we read, the pool paper, where they use the pre-trained text-to-image diffusion model to produce 3D objects and convert into a mesh. I just feel like we won't need this mesh stuff in the future. I know I say this a lot on this channel, but I feel like nerfs to me are going to eventually stand alone, and you won't need to constantly take a nerf and turn it into a mesh so that you can put the mesh in a video game. Method number 4, section 4. Rather than training on a single generative model to directly produce point clouds, we instead break the generation process into 3 steps. First, we generate a synthetic view conditioned on a text caption. Next, we produce a coarse point cloud, so 1024 points. This is their coarse point cloud, conditioned on the synthetic view, and finally they produce the fine point cloud, which is probably the final one here, or the one that we see in this image, and that's 4,000 points. So that's not really that much. How much size of point cloud for Velodyne laser? Okay, so Velodynes are it's a company that produces lidars, right? And these lidars are used in autonomous vehicles. You might have seen them sometimes. They're like this little spinning thing at the top, and they produce point clouds. And this is what a point cloud looks like, right? So each of these little lines here is actually made up of hundreds of little dots, right? So, for example, each of these dots here is a dot, and then they're classifying this point cloud usually, right? So they classify each point as either belonging to the road, or belonging to a wall, or belonging to a tree. So that's, when I think point clouds, that's usually what I'm thinking about. Kind of wish they had numbers about like how many per second, but either way, 4,096 points is a very small amount of points. They do not explicitly condition the point clouds on the text. To generate text conditional synthetic views, they use a 3 billion parameter glide model. Okay, we'll use our blue color there, since this is a number. Fine-tuned on rendered 3D models from our data set. What? I mean, I don't know. They say that their method doesn't require custom 3D data, but here you go. They're fine-tuning it on their data set. So what does that mean? To generate load, we use a conditional permutation invariant diffusion model. And then they upsample the point clouds. We train our model on a data set of several million 3D models and associated metadata. Okay, so they don't actually tell us what that data set is. That's just some random proprietary OpenAI data set. We found that data formats and quality varied widely, prompting us to develop various post-processing steps to ensure higher data quality. This right here is literally what your life is if you're a machine learning engineer. It's really just, you just sit there and make data clean. Because all the other stuff, like the transformer, the clip, like that's all done for you. So mostly what you're doing is just cleaning a bunch of data, which is what we saw in our Kaggle with ChatGPT series on that biology data. Is like we just spent all of it just looking at the data and dealing with the fact that it was huge. Rendered every model from 20 random camera angles using Blender. It's interesting. That's using Blender for synthetic data generation, and that's exactly what I was doing at a startup, which is interesting to see. They converted each object into a point cloud using its renderings, okay. Okay, so I mean, they're doing some kind of manipulation here. We clustered a dataset of clipped features, and then we averaged features over all renders. Yeah, this is something that I did for a project that I think is actually more and more common, and this is using clip to search and index data sets. So index, maybe not, but you can search a data set with text and then use the clip features. So you take a piece of text, you're like, I don't know, dog, turn that into a clip vector, and then turn every image in your data set into a clip vector, clip embedding, and then try to find all the clip embeddings that are close to the clip embedding of dog. And it actually works quite well. And here they're using it to cluster, so they take, they have 20 renders, 20 random camera angles for each 3D model, and then they average the clip features over for each of those 20 images, and then that clip feature roughly represents that image, and then they can cluster all the different 3D models, and then they can find, okay, some of these clusters are low quality, so it's a kind of a way to clean and filter through data sets. Okay, so they fine-tune for 100K iterations. Okay, this is figure 3 is for this section here, so we extend the framework to include RGB colors for each point cloud. In particular, we represent a point cloud as a tensor of shape k by 6, right? Where k is the number of points and the inner dimension contains x, y, z, and RGB. All coordinates and colors are normalized to the range -1 to 1. We then generate these tensors directly with diffusion, starting from random noise of shape k by 6 and gradually denoising it. Okay, so in something like a 2D image generator like Stable Diffusion, right? The noise, the ultimate noisy image, right? The final time step of the noising process looks like basically white and black and gray. And there's colors in there too, but basically it's 0 to 1 for RGB channel, right? Looks like noise. So what does noise look like in a point cloud world? Well, it's k, where k is a specific number of points, and then 6 dimensions, where you have the x, y, z, and then also the RGB. So it's interesting that they chose to do it all in point space rather than voxel space, right? So a lot of these 3D papers, they kind of break up the world into voxels, right? And then they're operating in the space of those voxels. Versus here, they're not. there's nothing that kind of forces these points, or maybe there is, maybe there's some kind of loss, but there's nothing that's really forcing these points to spread evenly around the volume of space, right? They could just all be right on top of each other. Although I assume they'll have some loss that pulls the points apart. Okay, so they have a transformer model that predicts the noise and the what's this capital sigma? I think they set it up here, right? Variance. Yeah. As input context, we run each point in the point cloud through a linear layer with output dimension d, obtaining a k by d input tensor. Okay. So they don't just, they have an addition, they turn this RGB XYZ into like an embedding of size d. To condition the image, we feed it through a pre-trained VIT clip model. Okay, VITL14 clip model. Take the layer embeddings from this clip model and linearly project it to another tensor. Final context to our model is of shape k plus 257 times d. Yeah, and this is what we noticed here, is that there's no positional encodings like explicitly or implicitly through the use of voxels, right? So the model is permutation invariant to the point clouds. It doesn't know about the relative position of these points. It's just kind of giving you a bunch of points. I'll be back 1 second. Okay. So here they say for image diffusion models, the best quality is typically achieved by using some form of hierarchy where a low resolution base model produces output which is then upsampled by another model. I think that's definitely true. We saw that in a bunch of the papers that we've read where basically diffusion is going to, the size of the image is going to be a huge factor in determining kind of the speed of inference and the speed of training. So in these kind of diffusion pipelines, usually what they'll do is they'll either diffuse in a small version of the image or sometimes directly in the latent space is where they'll be doing the diffusion because it's smaller dimensional. And then they'll have some kind of upsampling, either upsampling the small resolution image or just going from the embedding into an image. Yeah, so they have, for example, here, they do the same thing with the point cloud. So they tell you it's 4 times more expensive to generate 4,000 points than 1,000 points. For rendering base, we do not render generated point clouds directly. We convert the point clouds into textured meshes and render these meshes with Blender. Okay, to convert the point clouds into meshes, we use a regression-based model to predict the signed distance field of an object given its point cloud, and then apply marching cubes to extract a mesh. So they're telling me this is a mesh. I don't think this is a mesh. I think this is a bunch of circles are the mesh. Each sphere is its own little mesh. And it has its own little texture. But I don't think this whole object is one mesh. I don't know, we'll see. Appendix C. In the following sections, we conduct a number of ablations. We adopt the clip R precision metric for evaluating text to 3D methods using the same object-centric evaluation prompts. Here you go, the Frichet inception distance. Except now they have point cloud versions of these. So if you've watched any of our previous videos, I have a personal beef with FID as a metric to determine the quality of subjective things like generated images and generated models. It's a rant that I've kind of gone on a couple times, where I think that the user studies where they have people compare images or compare 3D models, I think those are better for something like this where it's kind of subjective. But it's expensive and it takes time, so IS and FID are kind of easy quantitative things that are somewhat accepted, but not. I still hold out that they're bogus. Okay, so they train a couple different ones. They have a 40 million unconditional, which is small model without conditioning. They have 40 million TextVec, small model which only conditions on text captions. Okay. Text caption is embedded with clip. 40 million with an image vect. Okay. So this is basically the clip, the image embedding of the image being used to get a clip embedding, and here you have the text being used to get a clip embedding. 40M, full image conditioning through a grid of clip latents. I think what they mean by grid of clip latents here is the fact that they have 20 random camera angles, and then you're going to have a different clip embedding for each of those camera angles, and then all of them together. I think they're calling that a grid. And then you have your big model, 300 mil here. Okay, let's use our quantitative color here. We have a 40 million model, which is small. You have 300 million, the medium, and then you have the Papa Bear here, 1 billion parameters. And you could probably bet your ass that all these pictures are from the 1 billion model, which is going to be the big one. Okay, common failure modes. Okay, so basically you have just kind of proportions being wrong, and then the things that are hidden from view, it kind of imagines them weirdly. Here you have your their different score, so the Frichet inception distance, inception score, and then their own kind of version of that, which they're calling clip R precision. And then you can basically see the general trend here is that the billion model, the big one, is better. So performance correlates very much with model size, which I think pretty much anybody in deep learning and machine learning world understands that now. Where the bigger your model is, the better it is. The more data you use, the better it is. The longer you train for it, as long as it's bigger and has more data, the better it is. Using a single is worse than using a grid. Find that PointE can produce consistent and high quality 3D shapes. Oh, sorry about this, M9. I just am not paying attention and I just forget that you ask questions. Yes, the filters for Chat GPT are likely not part of the actual model, but heuristic code logic that is added on top later. Fine-tuning a big model to have specific responses to filter specific is quite difficult, maybe even impossible, without affecting performance in other ways. Is point space interpolated between set views? I'm not sure what you mean by that. I think that you're talking about point cloud space, and then they have the 20 views. The point cloud space is probably relative to the camera angle, or the camera position. Or globally, since there are 20 different camera views. For large models, does it reach a point where further training is negligible? Yes. There is a point where if you continue to train your model on your data set, it will get worse. This is known as overfitting. With really big models and really big data sets, though, such as Chat GPT, I think overfitting is less of a concern. In that case, it is more about how much budget a project has to spend on training. Hopefully that kind of answers your question. Point space, do they generate it from standard views, e.g. then the model generates directly in point space. Once you have the point cloud, you can render it from any arbitrary view. Okay. Okay, going back here. Model's ability, well, correctly. Sometimes the point cloud diffusion model fails to understand or extrapolate. Text conditional 3D synthesis is a fairly new area of research. There's not yet a standard set of benchmarks for this task. Don't worry about it. No problem. Thanks for asking questions. Some current state of the art. Okay. Comparison of PointE to other 3D generation techniques measured by clip R precision. Again, I don't really know if clip R precision means anything here, but you have here two different transformer models. You have a slightly bigger one, and then you have a smaller one. Dream Fusion, and they're comparing the speed here around 12 V100 hours. Okay. And this one is 1.5 V100 minutes. So I said this at the very beginning, but they said that their model only takes a couple minutes to perform inference, but it's also on a V100, right? These V100s are not consumer GPUs. Those are expensive GPUs. So realistically, it's still going to be very difficult to use your consumer GPU and get these kind of results. Okay. While our model is a meaningful step towards fast text, it also has several limitations. Currently, our pipeline requires synthetic renderings, but this limitation could be lifted in future by training 3D generators that condition on real-world images. Yeah, I would say since they're not conditioning on the camera pose either, I think that's a good way to not have a limitation on synthetic data. A lot of times when people use the synthetic data, since they know the camera pose exactly, they can condition on that or use that in their pipeline. But I don't think they do that in this paper, which is a nice touch. High quality 3D representations such as meshes or nerfs. Yeah, I would say nerfs to me is where it's all at. Meshes and point clouds will eventually disappear over time, I think. Biases are inherited from the data set. Sure. PointE is capable of efficiently producing diverse and complex 3D shapes. Nice. Huh. They used ChatGPT for providing useful writing feedback. That's quite cool. I like that. I wonder what we could do with that. Let's do. I wonder what happens if you like copy. Let's go here. We can copy up here at the top. You copy this, put it in here. Can you help me improve the grammar and wording of my abstract for my scientific paper? See if we can copy it. Oh, look at that. In this paper, we explore an alternative method, and then here they say, in this paper, we present an alternative method. Our method first generates a single synthetic view. While our method still falls short, and then here it says, while our method falls short, so it gets rid of the still. It's kind of cool. I like that. You can use ChatGPT to basically clean up your paragraphs. Okay, let's look at these hyperparameters and look at this appendix here. So here in the appendix, they have their different parameters. So train all of our diffusion models with a batch size of 64 for a total of 1,300,000 iterations. Total of 1024 diffusion time steps. That's a lot of diffusion time steps. I think the paper on PointE, I think it was called, where we were looking at a diffusion model that was doing it in one time step. So 1024 is a lot of time steps. We produced 10K samples using a stochastic full noise. Okay, we use 64 steps. Use the hewn sampler. Okay, this is the width and the depth of the different transformer models here. So you can see how the width changes here from the 30 million to the 300 million to the 1 billion, and also the depth of the model, right? So you have 12 layers at 512 wide, and then the 1 billion you have over 2K layers at 24 layers deep, and you're training it with a comparatively much smaller learning rate. We apply random rotations to each point cloud and we add Gaussian noise to the points. Okay, this is how they actually go from point clouds to meshes. Okay, so they have an 8-layer encoder which processes the point cloud as an unordered sequence. Yes. The model outputs each token at a time, since what it is ultimately doing is next token prediction. This likely happens faster in the back than what is printed in the front end. I agree, it is likely slowed down a bit for dramatic effect. Sign distance function. This is also how they do meshes from nerfs. A subset of 2.4 million manifold meshes. I wish they told us what this 3D dataset that they have is. Like, why don't you give the people that? Points outside the surface have a negative sign, right? That's what the S in SDF mean, right? It's a distance function, but it's a signed distance function, and the sign means that it's either going to be positive if it's inside or negative if it's outside. Yeah, so this is the actual mesh here. This is what I was saying. So this is just a point cloud where each point is rendered as a sphere where each sphere itself is a little mesh. But this here is an actual mesh, right? So this is one contiguous mesh with a color or with a texture applied to it. But these images here, which are the ones that they have in their thing here, these aren't a single mesh. These are 4,000 little sphere meshes. I think it's important to realize that. They did an 80s terminal style cursor effects. Yeah, I'm sure they have a whole team that is human computer interaction people, you know, like people that try to, like, they're almost like psychiatrists, or like they try to figure out how neurologists, you know, like how a human should interact with an AI in a way that's like kind of interesting. And yeah, it's probably like hand in hand with the safety team you know? But yeah, the interface point and the user experience between AI models and then humans is definitely a growing field. Interesting, adding a border around can improve the reconstructed shapes. So these are interesting, the figure 9. This is pure text conditional. So it's also not even the big one. It's 40 millions parameters, so it's the smaller of the models. And then there's no images being used to condition this. They're just feeding this text, a laptop computer, into clip, and then getting into clip vector, and then using that clip embedding to generate points. So it's kind of interesting. Cool. This is a cute little paper. I like it. I don't think 3D point cloud generation like really necessarily matters, especially if you're generating this kind of stuff. Maybe there's applications in autonomous vehicles for generating kind of example point clouds and synthetic data for LiDAR systems and structured light sensors. But then even there, I think in autonomous vehicles, a lot of people are kind of adopting the idea that maybe you can just do it all with cameras. You don't need to have these $100,000 LiDAR systems on top of cars. So I don't know. I don't know where point clouds go. Honestly, I think out of the different 3D formats, to me, point clouds are the ones that are going to phase out the quickest. I think point clouds phase out first, then eventually meshes and textures fade out, and then you're left with a nerf future. So to me, this is almost more just kind of novelty. They kind of did something cool with the little toy problems, and they have their little cool renderings here, or cool little stuff that they generated, but maybe not a ton of real world use case for this. And that's probably why, realistically, why they have MIT license on this, right? If there was a real world use case for this, they wouldn't really put MIT license on it. But yeah, glad that they released the paper, glad that they put it on here and they let people use it. I kind of wish they would have told us what this 3D data set that they used, that they say millions of 3D asset data sets, right? They spent the time to clean it and make it nice, so why not release it? But other than that, cute little paper, and yeah, maybe we try the code for this tomorrow. I'm curious, but definitely not going to do that on this Windows computer. If anything, I would do it on my Linux computer. Cool. Thanks for watching the stream. Thanks for asking questions, M9. And